Looking at the various topological aspects of the real line, and every time we are trying to see how we generalize this in the general notion of metric spaces also. We could do more than that, but we'll stick to metric space level. Okay, so we first had the open sets in R, and then we generalized it to the notion of open sets in the metric space. And then we have the closed sets in R, then we have the closed sets in the metric space. Then we have the notion of a dense set R, namely the rationals, and that we generalize the notion of dense set in omega. And then the dense set in R was countable. So if we had a countably infinite dense set, we had the notion of circular. So each one of the abstract topological notions come out of one or the other property of the real line. The real line, or in more generally you will see finite dimensional space, L2, N or LP, N. These are the sort of motivating things for us for all these definitions. Now, I want to look at one property that we had for the real line, at least it's called the Cantor's intersection property. We had it at least for closed intervals so far. So let me recall this is a very important topological property. We will abstract and generalize further. The following Cantor's intersection property for, I'll just write closed intervals. What does that say? That says, if we start with, so JK, AK, BK are closed intervals in R. What does that mean? This AK and BK are real numbers, AK less than BK, and K runs from 1 to S. So we have a sequence of closed intervals in the real line such that one, they are non-increasing. JK plus 1 is either at best the same as JK or something smaller than JK contained in JK, and the length of the JKs, which is BK minus AK, tends to 0 as K. The lengths of the intervals are shrinking. They are going down to 0. This is all the hypothesis. The conclusion was that J, the intersection of all these JKs, is a singleton. This we have seen, we are going to see again. I am going to give again a proof of this. We will now write a proof which allows us to see how this could be generalized for metric spaces. So our aim is, the first aim for today is to generalize this result for a metric space. For a general metric space, how does this result look like? Now I want to start with the first question itself is, what is the role of a closed interval? How do you generalize the notion of a closed interval? That itself is, so first of all, how should I, first question, how should I generalize closed intervals? That's not difficult in a sense. If you look at JK, well, let's take any closed interval J, look at any closed interval AB. Now take the midpoint, and then call R as the length of the interval, half of that. Then we can write J as simply A minus R, M minus R. So I want to write that in a standard form, which I can now write as the set of all x in R such that the distance of x from M is less than R. We can write it as the ball of radius R about. So, and it is less than or equal to R. So it is this. So therefore, we will generalize the idea of a closed interval as a closed ball. Okay. So therefore, instead of starting with a sequence of closed intervals, we will start with a sequence of closed balls. Okay. So let B R N X N, let us call it as Bn. Okay. Center XL, radius Rn. B, a sequence of closed balls in a metric space omega d. Having done that, we would like these properties such that one omega k plus 1, bk plus 1 is contained bk, they are non-increasing. Okay. Each ball is, next ball is smaller inside. Then and what is this length? It's just the diameter of that ball. Or so we can simply say Rn goes to 0, the diameter goes to 0, the radius goes to 0. That's what we want to say. Then can we expect B equal to intersection of all these Bn's to be a singleton? Can we expect this intersection to be a singleton? This is the generalization of that question. Okay, so we replace the closed intervals by closed balls, decreasing, non-increasing by non-increasing, diameter going to 0. So here the intersection was a singleton. Is the intersection going to be a singleton? So now what I am going to look at is, we will look at a proof of this and see, go on writing the corresponding version how it will look in a metric space. Okay. And see whether it carries through. If it doesn't carry through, somewhere it will have to collapse. for whatever reasons, we'll find out why. Okay, now we have to locate the dust. Did we see a duster anywhere? That's more problem. Okay, so what I am going to write is proof for interval here. First interval case. That is the R case. There is a case. I will now write the metric space. I will erase this also, these conditions are clear. So the idea is fairly simple. What you do is, let's pick any point yn in J. It could be the center. The easiest way is work with the center of Jn itself. Okay, but let's pick any point yn in Jn. That's not no problem. Let's pick any yn. That was n. Turns out, we'll see what happens. Okay. Turns out, this is the first step. We'll prove this statement. Turns out, the sequence yn, from each one of these balls, each one of these intervals we pick a representative point. You could repeat the same point as I don't care. And from each interval, all I want is yn to be in in, J. Pick any point yn in in. Turns out that this is a Cauchy sequence. So the question we'll ask is, will yn be a Cauchy sequence? Suppose yes. Then we can copy the next step of the real line proof. Okay. The real line, then this happens. In the real line, in R, every Cauchy sequence converges. What do we call this property?
Complete.
The real line is complete. Because R is complete. Therefore, yn converges. So whenever I say R, I mean always the usual metric, unless otherwise stated. All these are the usual metrics. Okay. Many times I myself make objections when entrance exams are set, papers are set. People write, let F map R to R be a continuous function. Well, continuity depends on the metric that you have, but specify what metric you are using. The function must be not continuous with some other metric. So you have to be very specific when you talk about topological properties. What topology are you referring to? Here are the metric topologies, and therefore you must tell what the metric is. And in all these cases, I mean the usual metric, modulus, absolute x minus. Okay, now what will happen in this case? We have an arbitrary metric space. We do not know whether it is complete or not. So now we make a hypothesis. Let us assume that the metric space is complete. Then proceed, because we are stuck here. Okay. So assume omega d is complete. So this is a hypothesis you will have to add extra in the metric space case, because we don't have it for granted, unlike in the real case. In the real case, it was a very special, specific, concrete metric space. We already knew its properties. But a general metric space, we are not guaranteed it is complete. So assume that it is a complete metric space. Then Yn converges to Y psi. I use the symbol psi there in the metric space. It is the point I converges to psi. The last step turns out can show intersection E, intersection J is exactly psi. Okay. Then we will see whether that proof carries over. Can we show then intersection Vn? That's all there is to it. The proof is going to be a verbatim copy of the real line. We go on, except in some places you are stuck because real line has extra property which we do not know whether a general metric space has. The only thing that will be common that we can copy is wherever the absolute value metric is used, we can replace it by a D metric. That's all we can carry out. Alright. Now, what is the first step? First step is no problem. We can certainly pick a Yn in each Jn because that itself is an axiom of choice. Okay. There already axiom of choice is used. That given a sequence of sets, we have picked representatives, we have formed a parliament out of them, and that's the axiom of choice. Okay. So there is an axiom of choice in the proof. So the thing is, this axiom of choice is such an innocuous looking thing, but it's everywhere there. We take it for granted, but unfortunately we can't take it for granted. It has to be made as an axiom, and unless you work in axiomatic set theory with axiom of choice, these are all not valid. Your first step itself you are stuck. Okay. So, we have to show that Yn is a Cauchy sequence. What is it that we have to do for this? To do this, we need to show that for every epsilon positive, there exists an n epsilon such that n and m greater than or equal to n epsilon implies modulus of Yn minus Ym is less than epsilon. Is that difficult?
When the subset is keep on shrinking to...
Yeah, because the subsets are all shrinking. Beyond a certain stage, all the points will be in intervals of length less than epsilon, and therefore it is done. Okay? This follows, okay, let me just write therefore. This can be easily seen using Jn or non-increasing and length Jn goes to 0. That's important. The length Jn goes to 0. That's where it is important. The length Jn's will go to 0. One inside the other. So beyond a certain stage, all the points are going to be chosen from some small interval whose length is very small. So the distance will also can be made very small. That is the basic idea. Okay. So what does it mean? So, okay, let me just point it here. The length of Jn tends to 0. Therefore, there is a Jn whose total length will be less than epsilon by 2. We can do that. Beyond a certain stage, the length will be small. So there is an nth stage at which the length will be less than epsilon by 2. If that is so, all the subsequent j's will be inside this because they are non-increasing. So jm will also be here, jm will also be here for nm greater than or equal to n. If both of them are inside, the distance between any two of these points, what can be worst case? One sitting at this end point, the other sitting at that end point. The total can be at most epsilon. Okay. So therefore Yn Ym belongs to Jn, therefore mod yn minus yn. You make it as an epsilon by 3, which is a closed interval, it could become epsilon, so 2 epsilon by 3. Doesn't matter. Okay, so what is that? So now is there anything wrong in that proof carrying it over here? The same thing. There are these closed balls now, one inside the other. The diameter is going to 0, the radius is going to 0. So beyond a certain stage, there will be a ball of radius as small as you want, and all the points are going of the sequence are going to sit inside that, and therefore their distance will also be less. So can easily, this is what is meant by a mathematics teachers could easily see that this is true. Just the same argument as in frequency. Okay? Now, in the real case, next step is, because the real line is a Cauchy sequence, the sequence converges to 1. Now we assume that it is complete, and therefore it is going to converge to this side. The last step is to show that this point lies in the intersection. Do you see that? That this point lies in the intersection.
Because the point belongs to every section.
That is exactly what you have to show. That the limit belongs to every point. That the limit belongs to every point is what we have to show. Why does the limit belong to every interval? Can somebody suggest what is going on? We want to show that here we have to show that
So AN and BN are themselves Cauchy sequences. The endpoints of the intervals.
okay.
Suppose not,
For they have a limit.
Suppose not, yes.
then you can find one point.
Let me write it, okay? Suppose not, especially write, suppose here itself, suppose not,
Then inside that interval and the limit, there will be some gap.
where?
I have in that, suppose it don't belong to some interval.
Okay, so suppose not, then there exists say n naught such that psi does not belong to Jn naught, right? Right, then
Then the gap between the midpoint, the boundary, that has to.
let's say An naught Bn naught. Then
Then we must get some xi which outside this. Limit is outside this. Xi is outside this line.
psi is outside this.
Then we can have some other capital N so that we get the limit inside.
Now what happens to Yn naught? It will be inside this, okay? And what happens to subsequence wise? Where will be the subsequent wise?
All between the Jn naught and
Between that An naught and Bn naught. That means beyond a certain stage, the y's are staying away from psi. That will mean that psi is not a limit point. Is that clear? See, let me write this proof. Suppose not. That means it does not belong to the intersection. If it does not belong to the intersection, why I asked was, I know a proof, I will write my own way, but I want to see. Incidentally, I had a topology teacher who did the following thing. On the first day, he handed us over about 8 pages of notes. it contained all the first 2 pages contained all the basic definitions, and the next 6 pages contained the important theorems in topology. The rest of the course was on any day of the class, any student can attempt to give any proof of any of the theorems. And he would just sit there and see the others participate and see whether finally the proof has come and whether that fellow has convinced others that he has a proof, etc., etc. Eventually all the theorems are proved by the students themselves. There was no way the teacher gave a proof. And any student at any stage of the game presented the proof of the last theorem, he already got the grade for the course. He can attend the rest of the classes or not. Because the last theorem, we stated it in such a way that every idea was used. So if we had understood every idea and put them together and proved that theorem, he is through. So sometimes, otherwise, what is it? We have some standard ways of writing, like epsilon greater than 0, etc., etc., etc. Anyway, so sometimes it's better to get the proof from the class. Okay, this is a different way of looking at the proof than I had. Okay, so that's the real. Suppose not, then there exists an N naught. Because it does not belong to this intersection, it should not belong to at least one of them. If it belongs to all of them, it will belong to intersection. So there is at least one fellow to whom it does not belong. So there is a J N naught said that Xi does not belong to this. So Xi stays outside this. Therefore, since n greater than or equal to n naught, for n greater than or equal to n naught, Jn is contained or equal to Jn naught, it follows Xi does not belong to Jn, and hence distance of Yn from Xi will be at least distance of this interval endpoint from Xi. Do you see that? Xi could be on that side or this side, I don't know which endpoint. So this positive distance is there from all the tail of the sequence to Xi. Now if they stay at a positive distance away from Xi, they are never going to hit Xi as the limit, and therefore Xi cannot be a limit point, a contradiction. Therefore, Yn, because I was. Now, what is the way of carrying it out there? Is there any problem carrying it out there? The same story goes through again. Okay, instead of the closed intervals, you have to simply write the balls. Okay, same. No. Now what have we shown here? We have only shown that Xi belongs to the intersection. There could be something else also in the intersection. So this only shows, okay, suppose naught is not correct. Well, first show that. Therefore Xi belongs to the intersection Jn. So therefore Xi belongs to the intersection Bn. But we are not yet shown that that is the only thing that's in Bn. Next to show eta belongs to the intersection Jn implies eta is equal to 0. Anything that belongs to the intersection cannot be anything other than Xi. So Xi is the only point that belongs to the intersection. Anybody else who belongs to Cn has to be Xi only. Nobody else can be in that intersection. Now how do we show that? I will again write. To show, the trick to show two fellows are equal is to show that the distance between them is 0.
Yeah.
So all you have to show is mod eta minus I
Sir, can't we define a singleton as an interval with two endpoints as the same?
It could be.
So then if an and bn being the endpoints of each sequence j,
See,
interval
if
j,
you are talking about the endpoints, you have a problem about generating this to the metric space. You have a surface of a sphere at the boundary, isn't it? So that problem will be there. Otherwise, I have that the ANs are a non-increasing, non-decreasing sequence, it's bounded above, therefore, I already given that proof. That problem with that proof is you can't push it any further. The way, if you look at them purely as balls, that's the way that you can generalize it to a metric space. You cannot look at them at the end points of the interval, then you have to look at the entire surface and things like that. So, and a crazy way that generally we show that something is zero is to show that it is less than epsilon for every positive epsilon.
Even here we can say if it is not, then there is a positive distance between them. And since eta and xi belong to every of them,
Yes.
they cannot come to
That's what I mean. You can do it in 150 ways. Okay. So I am just writing. Generally, the trick is to show that less than epsilon for every epsilon, and that's what you do. Exactly same proof you go. Okay, try that and carry on. So what is the conclusion? The conclusion is, if in a complete metric space, the intersection of a non-increasing sequence of balls whose diameter goes to 0 must be a singleton. That's what the Cantor's intersection property for closed balls in a metric space. So what is the theorem? This is called the Cantor's intersection property for closed balls in a metric space. So in a complete metric space, if is a sequence of closed balls such that those conditions are satisfied, the diameters or radius is going down to 0, then the conclusion is intersection of B and singleton. Actually, the singleton is the limit point of the centers of these balls. Like I said, you pick any point inside that, and the limit xi will be the limit point of all those points. I could have picked the points in Bn to be the centers. So yn is going to be chosen as xn. So the xn's, so the centers will converge to that limit point. So the centers of these balls give us a good approximation for the intersection. The larger the n, the better the approximation. Now, that hypothesis of completeness is crucial. This result could fail to be true in an incomplete metric space. So in an incomplete metric space, this need not be true. The metric space which is not complete these people because that crucial step where we had that the YNs converge, they formed a Cauchy sequence and therefore they converge. That step is a real problem. So now try to, I'll just quickly point out what you can do. Take Q with the usual metric. So the distance between two, the Q is the set of rational numbers, the usual distance, take this usual metric and try to construct a sequence of fellows whose center does not converge to a rational number. So what you should do is take centers which are converging to root 2 and then construct your intervals appropriately, and then you will find that you have a sequence of closed intervals coming down in the closed balls coming down in the rational number space, the diameter going down to 0, but the centers are all converging to root 2, which is not a rational number, and then you are in trouble. Okay, so that intersection point is not in the metric space, and there will be intersection bit. So okay, let's say for example take root 2. There is a point called root 2, the real number root 2. Now there is, the rational numbers are dense, so there is at least one rational number which in a distance of 1 from root 2. And similarly there is a at least one rational number, so let's say half, whatever, Q1, Q11, let me call it L1, R1, left and right hand, to remember. The distances are 1s, at most 1. Then having chosen these 2 points, take your first interval to be this. Okay? So there is a rational number within a distance of 1 on the right side from root 2. There is a rational number within a distance of 1 on the left side of root 2. Pick any 2 such numbers and take that to be your first interval J1. So what is your ball? Not interval, no, what is the ball here? First ball you choose is the set of all x in Q such that x belongs to L1 less than x less than. This is the ball, the rotation R is there, I use R for radius. Next what you do is, look at this distance and this distance. Whichever is small, take half of that distance. Then you will find a rational number here and a rational number here within that half distance. So what is the distance between these 2 fellows? There will be less than half the maximum distance, the minimum distance of these 2. So suppose root 2 L1 is some S1, R1 minus root 2 is S2. Look at minimum of S1 and S2 and then take half of that and find a rational number within this distance here and within this distance here. Then take that as the second interval. What is the third interval now? That's a bootstrap operation. Do the same thing with this internal interval now. Find the minimum distance, take half of that and so on and so forth inside. Now what do you get? You get a sequence of intervals, one inside the other. The diameters are getting half every time. So there will be some k by 2 to the power of n. They will go to 0. What is the intersection point? Root 2, and which is not in Q. So the intersection is empty. It's not a singleton. Okay? So the intersection of these giants will now be empty because root 2 does not. Because all this we are looking at only the points in, we call it P, all only points in Q. All our universe is Q, and that fellow is that limit point is not in Q, and that's where the completeness comes into the picture. Okay, so the completeness is a crucial hypothesis in this theorem. If completeness were not there, this intersection could turn out to be empty. Okay, that's the first thing that I wanted to observe. I will finally further look at more and more different raised up versions of this Cantor's intersection property. Right now the intervals we see these things clearly. From intervals we see it more clearly for words. That's all. We will see it for more little more trickier situations or more general situations. little later, by the time this result would sink in the mind. Okay, there are one or two simple remarks about that, which I will do before I go to the next important property of the real line, and then see what would be happening in the metric space situation. See, sometimes you cannot take for granted. See, this is what happens when your real line or a finite dimensional, essentially finite dimensional things are clear. There is a certain hope for you to see, put your leg into the infinite world and see what could happen, an abstract world, and see what happens. Because you have some idea of what could happen and try to push that, and wherever there is a trouble, you know what hypothesis you need. Put the right hypothesis, it will work. And that's where, most of the first 40 years, 35 years of the 20th century development in operator theory and analysis was basically linear algebra and finite dimensional calculus. Just simply push through in a nice manner wherever there was necessary hypothesis needed, the right hypothesis was put. Right. Now suppose I have a metric space. Now I can work in this. We define, suppose S is omega, S is a subset of omega, and x naught is a point of omega. It is the limit point of S. What does it mean? If you take this point x naught and draw any ball of radius epsilon, so for every epsilon positive, if you look at the ball of radius epsilon, center x naught about this point. Now I am not putting the closed ball, I am looking only at the internal ball, not the distance from x naught is not allowed to be equal to epsilon, only less than, what do you call it, the hollow ball or whatever, not hollow ball without the cover.
Open ball.
Open ball, okay. That I wanted to avoid that word, okay, doesn't matter. Open ball. There is no opening in the ball. Open ball. Anyway, you know what it means, okay. That is the set of all points x in omega, such that d of x naught is less than epsilon. Right. If we take any such ball, there will be at least one point of S which is lying there, will be different from the center. If the center possibly is in S, but in addition to the center there will be at least one point. So there exists S in S, S not equal to x naught, such that S belongs to x naught. Okay, that is what is meant by saying that x naught is the limit point of the set S. Now let me draw a bigger picture of that, blow it up. Here is x naught, here is epsilon. So given the epsilon and the limit point x naught, I draw a ball of any radius, the given radius epsilon. So now what it says is, x naught is a limit point, then there is a point, I pick one such point, again axiom of choice. Okay. I pick one such point, S1. So there exists S1 in V epsilon x naught intersection S, S1 not equal to x1. Okay, there is a point of S which lies in S. Now, look at the distance between x naught and S. What can you say about the distance between x naught and S? That certainly cannot be 0. Why? Because S1 and x. Because S1 is not equal to x naught. The distance is 0 if and only if the 2 points are the same. So therefore I can choose epsilon 1 to be dx naught S1. That's a positive. Now what I will do is by 3. 2 is enough. something, anything, you multiply d by a number which is less than 1. Okay. Now what do? Choose this, look at this, b epsilon 1 x. What is that? Let's draw a smaller sphere. This is epsilon. Picture is terrible because 1/3 it looks so big. It has been drawn 1/3, the inside part has been blown up. Okay. For convenience. This is topology. Non-uniform blowing is allowed. Non-uniform expansion and contraction is allowed in topology. So that I am using. Okay. Now, still x0 is a limit point. Any ball around it must have a point of S. So there must be a point of S inside this also, because x0 is a limit point. So there exists a point, since x0 is a limit point. Whatever ball you draw about x0, there must be a point of S. There exists a point S2. Certainly it is not S1. It is also not equal to the center. S2 not equal to x0 and S1, such that S2 belongs to B epsilon 1 x0. And if it belongs to B epsilon 1 x1, it also belongs to B x0, because that ball is inside this ball. Now what is this? This is typical thing. Once you have two samples, repeat this process. Now inside, what do I do now next? Look at this distance, I have put the points S2, repeat this process for this now. Look at the distance between x0 and S2, take 1/3 of that, draw another ball. Inside that you can pick another point, okay? So dot, dot, dot. You know how to define by index. You get a sequence of points S1, S2, etc. belonging to S in Vx. All of them are Vx. The balls are shrinking. Now what we have got is the following. If x0 is a limit point, then first we said every ball has at least one point. Now we are able to conclude every ball must have an infinite number of points of S inside them. So therefore, x0 is a limit point of S implies for every epsilon positive, B epsilon x0 intersection S is infinite. Previously we were very cautious. We said only one, but now we are able to assert that there is an infinite number of points. Is the converse true? Well, if it has an infinite number of points, certainly it has 1 point. Our definition needs only 1 point. So therefore, the converse is also. A point is a limit point if and only if every ball around it has an infinite number of points of the set. Then only it's a limit point of that set. Okay. Basically here also there is this intersection property coming into the picture in some sense. Right. So therefore we can think of the definition of limit point in a slightly different way. It sometimes it's easier to show that there are, easier to see that there are an infinite number of points. Basically we are assured that every neighborhood of the point is rich of points of S. There must be an infinite number of points of S. That's what it means by limit. Okay. There is one more property of the real line, that we will see first, and then we will see what sort of generalizations we have to apply. It will be little tricky generalizations that we have to look at. Now suppose you consider an infinite set on the real line. The moment the previous result says that if a point has to be a limit point of a set S, every neighborhood of that point or every ball about that point must have an infinite number of points of that set S. Not only that, these are infinite number of distinct points, because we choose S1 which is not equal to S2, not equal to S3, not equal to S4, etc., etc. So it must have an infinite number of distinct points. Therefore, if you have a finite set, there is no chance of a limit point for that set. Because if you have a finite set, whatever point you choose, no ball can contain an infinite number of points. Therefore, there is no hope of talking about a limit point for a finite set. The question therefore is, what about infinite sets? Should they necessarily have limit points? And we immediately know if you take the set 1, 2, 3, 4, 5, 6, etc., the natural number, they don't have limit point because each fellow lives at a distance far away from the other. So there is no need for infinite sets also to have a limit point. But the problem with this set 1, 2, 3, 4 is they live at a positive distance from each other, and therefore there should be enough elbow room for them to move away. So that set goes off to infinity. Suppose we block that option and say, I am not allowing you to go off to infinity. I want you to be infinite. That is, I have a bounded infinite set. Then Bolzano says there must be a limit point. You are forced, because infinite number of fellows have to somehow adjust themselves within this finite space. They will adjust such that somewhere along the line they will crowd. It's like our traffic, Bangalore traffic. There will be a jam somewhere. Always there will be a jam in Bangalore somewhere, and that's this theorem. So, first of all, by our previous observation, it follows that no finite set can have a limit point. Let's look at R. Let us consider n in R. This is an infinite subset and has no limit points. Because this turns out to be because it is unbounded. Okay. What we now show is, that this is called Bolzano Cantor. Any bounded infinite set, subset of R, must have at least one limit. Now, I'll come to this, we drew this, okay? We drew this, did the same proof as the catching a lion in a Sahara desert by the bisection method. Okay, thanks to him, I got a copy of that book eventually, random box. Then, unfortunately, this doesn't carry over to infinite in metric space. There is a certain difficulty that comes out. We have to avoid that difficulty, and that leads to certain newer notions in metric spaces. So before doing that, we will first show that this result is obviously false in general metric spaces by giving an example of a metric space where this is false. Okay. This need not be true in general metric. Before proving this, I will state that clearly. Not clearly, I will say it. Remark. This need not be true in an arbitrary metric space. That is, in an arbitrary metric space, there is a chance that you may have an infinite set which is bounded but still does not have any limit point. The reason is the following. The reason is that we said the finite set need not have a limit point. We said that the infinite set, natural numbers went up to infinity, therefore they didn't have a limit point. And therefore we will hold them with a tight rope on both sides. Don't allow them to fly off to infinity on either side. Then they are trapped. So we say that somewhere some fellows will be trapped and you will have a limit point. But suppose, imagine the situation where those fellows can fly off in other directions. In the real life, we trapped them only in one direction. Suppose there are enough directions to fly off. And even if you restrict each direction, but if there are infinite number of directions to fly off, you are in trouble. Okay? And that's exactly what happens in the infinite dimensional spaces. So you may trap them, but there are enough movement space available, they move. That is, we can have infinite bounded sets that do not have a limit. Now the question is, I understand what is meant by an infinite set in a metric space. What is meant by a bounded set in a metric space? Well, for that I go back and see what is meant by a bounded set in a real life. In a bounded set in a real life, I simply mean I can trap all the members between minus m and plus m. That means I can trap the members of the set in a closed interval. So if I can trap the members of the set in a closed ball, I call it a bounded set. So what is meant by a bounded set? So a set S is said to be bounded if there exists x naught in omega and r positive such that S is contained in V r x naught. You can trap it like, well, if you can trap it in V r x naught closure, you can trap it in V2 r x naught without the closure. But that doesn't matter, let's keep it as it is. V r x naught closure. Okay? So then we say it's a bounded set. So just like trapping it in a closed interval, here trap it in a closed ball. There is sufficiently large big ball which traps all the members of the set, then that set is called a bounded set. Now let's look at the, I said this. Take for example, let me take L2R. Whatever, you could have taken L1 or L infinity or LPR, anything would have worked. Okay. L2R is our thing which are so-called finite energy, discrete, etc. etc. What does it mean? This is the set of all x1, x2, xn, that xj belongs to R, and summation, the energy is finite. this is the set of such vectors is called L to N, L to R. What is the distance between two such vectors? Summation mod xj minus yj squared, j equal to 1 to infinity, square the gradient distance. This is what is meant by L to R. For normal, usual, finite answer, put N, you put up to infinity. To take care of that everything converges, you put this hypothesis. Now, look at the following. Call E1 to be this vector, whose first coordinate is 0, 1, the rest of them 0. Obviously it belongs to L to R because the summation is just 1. Similarly, call A2, E2 to be the vector whose second coordinate is 0, 1. So in general call Ej to be the vector whose jth coordinate is 1. Okay. So like that, we have an infinite number of vectors. Call this set S to be the collection of all these Ej's. Okay. Now, what about if you take any two fellows in this set S and look at the distance, what will that be?
1.
It will be equal to square root of 2 if I not equal to j. Right? Because it will be 1 plus 1, the difference of the coordinates, and I am taking the square root, so it will be square root of 2. All these fellows are trying to stay at a distance away from, they are never getting close to each other. So can it have a convergent can it have a limit point? If it has a limit point, they must all get within say 10 to the power of minus 8 to that point. But they are all staying about a distance of 1.4 plus etc. from each other. And therefore there is no way this has a limit point. Okay? This cannot have a limit point. Therefore, S cannot have a limit point since D, EI, EJ or EN, EM can never be made less than say half, however large n is. NMR. Because that's always root 2. Okay? And therefore En is not even a Cauchy sequence. And no subsequence can be Cauchy. So there is no chance of some fellows come and sit within a small distance of each other. Okay? Well, we put together all these things. Therefore, S cannot have a limit. Now, I have not yet proved Bolzano Cantor theorem. What I am saying is that you will have I have to show that this is bounded. Is this set bounded? Yes, is bounded because S is contained in we take a ball of radius 1 about the point 0. Okay. All of them have within a distance of 1 from the origin, therefore they lie within that ball. In fact, they lie exactly on that surface. Okay, that's why we needed the closure also. Okay.
Sir?
Yeah.
Sir, the earlier example, if we take the earlier example, the set R and distance between x and y is 1 if x not equal to y and 0 else. Then that was
that's why I said usual topology. Q, it did not. That's why I always say that whenever I say R, I mean the usual topology. If you take some other topology, crazy things can happen.
Yeah. But in this one also, I mean, no limit.
In that metric space, Cantor's intersection property may be false, Bolzano Cantor theorem may be false, many things may be false. What I said was these are true in R with the usual topology with which we normally work, and we try to generalize this system. When you generalize an abstract metric space, it may become a problem. In the same R with a different metric, it may become a problem, as you just have pointed out. Whenever the metric is such that you have an infinite number of points sitting mutually at a constant distance from each other, you will end up in such problems. And the simplest example, to make everybody sit with at a constant distance from each other, which is the discrete metric is said. The distance between any two same points is 1, the rest of them is 0, and then everybody is sitting at a distance of 1 from each other. No matter what, you cannot bring them close. That's the. But that is why I said, whenever you talk topology, you must always say what is your topology. What is your metric if you are talking about metric topology? What is your norm if you are talking about norm topology? What is your topology if you are talking about a general topology? Without that, you cannot make a statement. It is with respect, this is a package. The set, the topology. If you are metric topology, the set and the metric. Together only I can, with this combination, this result takes place. Any other combination, if you change one of those combinations, if you take the same set but change the metric, the results may be totally different. Okay. Right. So now, S is bounded because it's in the closed ball radius 1 about the origin. So we have a bounded infinite set which does not have a limit point. So you can have metric spaces in which bounded infinite sets do not have a limit point. Now, what would have happened with this example if I had made this n component vectors? This example would not have worked as a counter example. Because how many such vectors you would have got? Only finite number of them. So this would not have worked. So there is hope still for finite dimensional spaces. Okay, you are not allowing them to fly off in too many places. Okay, so there is hope still that we may perhaps still get Bolzano theorem in finite dimensional space. As soon as they are true for R, you will see for L2 NR, or LP NR, or L1 NR, or L infinity NR. Okay. So the problem comes the moment you allow several directions for them to fly out, orthogonal directions to fly out. But still, controlled flying off on each direction, but there is enough maneuverability in directions, though the space is controlled.
What about
Huh?
Rn?
Rn.
Yeah.
Rn, you should not say Rn.
R.
Huh?
N-dimensional.
So therefore you must tell the topology.
Rn with metric.
That's why I said you should talk about L2 NR, or LP NR, or in general R, the L infinity NR. Either the 2 norm, the 2 metric, or the P metric, or the infinity metric. We will see that. That's what I said. There is still hope for these fellows. Well, we must make sure that it is true for R. See, once it is true for R, quite a large number of them can be pushed for finite number. See, moving from 1 to finite is easy. Basically what it says is, sometimes it is doing finite dimensional, n-dimensional thing is doing n one-dimensional things. Essentially, I mean, most of the ideas are the same. Somewhere along the line you have to do the patching up work, that's all. You do n one-dimensional things and patch them. So essentially they will boil down to n one-dimensional things, which are the R's. In R, each one of this metric is the same. Whether you take peak power and then take 1 over p, or take square power and then take 1 over 2 power, both are same. So in R, if the result is true, there is a good hope we can move up to finite dimension. That is done. It is the move from finite to infinite dimension space that creates all this. Of course, I should not even be talking about dimension, because we are not talking about a vector space here at all. We are just talking about it in a purely topological nature, but we are using some of these properties. So, well, now I will just indicate the proof of this. A bounded infinite set has, so let S be a bounded infinite set in R. This is crazy proof. This is how. Therefore, there exists a closed interval J such that finite closed J equal to A, and I call it A1, B1. I like this denotation such that S is contained. Because it's a closed system. Now what I do is, so let M1 be the, let me call L as the length of this interval. Choose one such interval which contains the set S, closed interval, and call M1 be the midpoint of this. Be the midpoint of J. Let's call it J1 itself. I will do this on this. M1 J1 plus B1 by 2. Okay. Now, what does that mean? I have two closed intervals. But A1, B1 has now been split into two closed intervals, A1, M1 and M1, B1. Now, S is infinite. If S is infinite, all of them lie here. So either this half or this half must have an infinite number of elements of S. If both of them have only a finite number of elements of S, then S will have only a finite number of elements. So one of the halves must have an infinite number of elements of S. Call it J2. Now what happened to J2? J2 is contained in J1 and the length of J2 is half of length of J1. They called it as L, is it? So it is just half L. Right? Now repeat that. Here is my J2. Let M2 be the midpoint of that. Okay? Then look at this. So M2 is midpoint of J2. So look at the two halves. Now there are infinite number of points of S in J2. So one of the halves must contain infinite number of points. One half, this is where we are getting close to the tiger. One half has infinite number of points of this. Call it J3. Well, both of them may have. It's very likely that both the halves have infinite number of points. In which case, choose any one of them as J3. Okay. Call it J3. Okay, so now what is J3? J3 is contained in J2. Length of J3 is half of length of J2, which is 1 by 2 squared L1. Continue this process. Then get a J4, J5, J6. So what do you get by this process? You get Jn, a sequence of closed intervals such that Jn is contained, n plus 1 is contained in Jn. And what happens to the length of Jn? It is L by 2 to the power of n minus 1. When it is 3, it's a square here. And then goes to infinity, this goes to 0. So we are in the Cantor's intersection property situation. We have a sequence of closed intervals, they are shrinking and the length is going down to 0 and therefore the intersection must be a single line. Implies Cantor's intersection property by intersection of Jn is a singleton. Okay. Exercise shows I is a limit point for this. Show that this psi Okay, so we're done. So we already got a limit point. Every infinite, bounded infinite set must have a. And that's what is known as the Bolzano theorem. And maybe another 4 or 5 days the lecture notes will be on the web, then the proof of this will be there, that it is a limit point. In the meantime, if you want to look at it, look at it. Right. So, now let's look at the finite dimensional situation. What happened? Somebody raised that question, so let me discuss it. Okay. Now, look at, I will just look at L2 NR. I'm giving the usual Euclidean metric, but all other metrics you can similarly work out the details. What does this mean? I am looking at all vectors in with the distance function as the usual what we are talking about in geometry. The difference in the coordinate square, sum over all coordinate, and then take the square. That's how we define the distance between the square. So that's what the finite dimensional situation is, Rn. But with this metric, we will see it with this metric. Now, we want to see that result. For that, we must look at any bounded infinite set. So, SB, any bounded infinite set. Okay? I'll just indicate the lines of the proof. I will not write all the details now. What is meant by bounded set? There is a sphere which contains the set S. So, suppose there is a sphere that contains this set. Let's call this as a, I'll just make things convenient for us. There is a sphere which contains this set. Now, the zero vector somewhere is sitting here. Right? So, certainly I can draw a big enough sphere about the origin which encloses this also, isn't it? Sufficiently large R. Look at the distance between this and x0 and add more than this R to it, and then that will enclose everything into that. Okay. So, without loss of generality, we have a ball, closed ball, P R 0. You can center it at the origin, closed ball, such that S is contained. Okay. The idea is the following. If you have S, it's an infinite set. We are having an infinite set. What does it mean? You have an infinite set of now n component vectors. Infinite set of n component vectors. Look at all the first components. What are they? They are all real numbers and they are infinite of them. Am I right? No. Because all of them may have the same first component. But it is in the second or the third or the fourth component they may change. If there are two possibilities, there are an infinite number of first components, or there are only a finite number of first components. Let us look at the second class. There are only a finite number of first components, in which case one of the components must be repeating infinite number of times. And therefore that fellow is himself a limit point of the first coordinates. Okay, is that clear? If there are only a finite number of first coordinates, but since we have infinite number of vectors, at least one of the coordinates must occur infinite number of times. That means that point can be thought of as the limit point of the first coordinates. Just look at it that way. Or just take that coordinate as the first coordinate. We are looking at a limit point, right? If we are looking at a limit point, we want to look at a vector which has n component as a possible candidate for the limit point. If one of the coordinates, first coordinates it repeats infinite number of times, take that number as the first coordinate of your candidate for the limit point. If by chance there are infinite number of first coordinates, distinct first coordinates, then all these are real numbers. So I have an infinite subset of the real numbers, and this boundedness will force the boundedness of the first coordinates also, and so I will have an infinite number of bounded real numbers. For them I can apply the Bolzano stress theorem. Therefore the first coordinate somehow is fixed. Take that limit point as the first coordinate. Repeat, go to the second coordinate and the nth coordinate. You got a candidate for the limit point. Now check, verify that that is indeed the limit point. Okay. So, you know how to write this proof? It is easy to see that. See that? Okay. 1. For any j, j, 1 less than or equal to j less than or equal to j, either 1, there are infinite number of distinct jth coordinates in the S vectors. Okay? Among the S vectors, there are infinite number of them have distinct, different coordinates, or there are only a finite number of distinct j coordinates among the S vectors. Okay. Now, in case 1, these infinite number form a bounded infinite set of real numbers. Why is this bounded? This says in any direction it can't extend up to more than r. It's a sphere of in our n-dimensional ball of radius r. Any coordinate cannot extend more than r or minus r. So each coordinate is also bounded by r. In fact, bounded by, that is mod xj less than or equal to r. The jth coordinate will have to be less than or equal to r. Therefore, by Bolzano stress theorem, these will have a limit point. Let's call it as xj star. In case 2, one of the jth coordinates must repeat infinitely often. Because there are an infinite number of vectors and if only finite number of the coordinates are distinct, somewhere along the line somebody has to repeat it. If everybody repeats only a finite number of times, there is a problem. There is one fellow must repeat infinite number of coordinates. One of the jth coordinate repeats infinite number of times, then take this as xj. So in any case we get an xj star. Construct the vector x1, x star psi to be x1 star, x2 star, because we can do it for each day. Prove psi. Now we can clearly see that x1 star is the limit point of the first coordinates, x2 star, so it can be made close enough to, the first coordinates can be made close enough to x1 star, second coordinates can be made close enough to x2 star, and so on and so forth. And since there are only finite number of them, the total closeness will also be small. In the infinite case, the problem was small number of infinite things need not be small. Small number of finite things is small, but small number of infinite things need not be small. That's the, so this is roughly the line of argument for that. So we have, now there was absolutely no problem about continuing this argument for LP, 1 less plus infinity, or even L infinity, L2 infinity, Ln infinity. As long as you have finite number of coordinates, boundedness as a vector implies boundedness component wise, and these now components are real numbers. Apply the real number theorem n times and catch hold of one candidate vector and prove that that is indeed the candidate. Okay, this is a typical proof. Okay, first catch hold of a candidate. Whenever you are looking for a limit, you are groping in the dark. You have to catch hold of a natural candidate who is the limit. To do that, you work with each one of the coordinates separately. That brings you down to earth to the real number system, and then you use all the power of the real number system to catch hold of the candidate, and then actually verify that he is indeed the right candidate, or at least a right candidate. Okay, I think that's time for me to stop.
So in H2 there could be two
There should be many limit points. What is Bolzano theorem? There exists at least one limit point. It doesn't say at most one.
So
limit.
what can repeat? I mean that jth code.
Take any one of them as XJ star. Right? Take any one of them as.
So here this only shows that means for every jth the jth coordinate has a limit point.
That's all.
But means when we combine them x1 star x2 star
That's
all
not
of them
proved.
so means this point
Prove that.
oh.
Because there are infinite number of points are close to this. Infinite number of points are close to this. First you take the first coordinates. Infinite number of them are close to this. Among those, infinite number of them are close to the second one also. Among those, infinite number of them are close to the third one also. That is how this whole argument has to go through. First finish the first coordinates and take those infinite fellows and do it for the second coordinates. Take those infinite number of fellows, do it for third coordinates, and go on and get to the nth coordinate. Okay. You have to slightly, you have to write these things carefully, and that is why I said it is easy to see that. Which means all those things you have to set right.